So here we will discuss how to draw the Bode plot for different kinds of transfer functions. That is analysis of the frequency domain sections using the Bode diagram. So these Bode plots are sometimes known as asymptotic graph. Asymptotic graph means whatever we will draw. In the last class we have discussed these slopes. So plus 20 dB per decade, that was plus 20 dB per decade, minus 20 dB per decade, plus 40 dB per decade, and all these things. These are the defined slopes we have already talked about. So if these are the slopes, what is the contribution of it? That means we are going to get a straight line approximation of the actual graph. So actually, if you vary the frequency, may not be all these graphs, all these magnitudes will be following the straight lines. But actually in Bode plot, what do? We do the asymptotic graph. Asymptotic graph means that the approximation to the straight line, that is straight line approximation of the actual graph, straight line approximation of the actual graph, and that is why this is known as the asymptotic graph. And when you will go for the drawing of the Bode plot, what you consider first of all, the thing is that here we have to consider the transfer functions to be this is minimum phase. That is very important. The concept of minimum phase is that I am giving some examples. Say gs is equal to s plus 1 by s plus 2 into s plus 4. See, what are the poles and zeros? You see, poles at -2 and -4 and zeros at -1. That means all the poles and zeros you can place in the left hand side of the S-plane. If any system having all the poles and zeros to the left hand side of the S-plane, so that system is known as minimum phase. And for Bode plot, this is one of the major criteria. If the system is only minimum phase, then the Bode plot is possible, right? So if the system is only minimum phase, for non-minimum phase system, we have to go for Nyquist plot. So Nyquist plot actually, or polar plot, by using that tool, we can find out the system stability for any kind of system, like minimum phase system and non-minimum phase system. And for Bode plot, we will have to consider the minimum phase system. Why this minimum phase system is very much important, that I will discuss here. So here we will start with one example, and we will go studying all these theories, background of it, and finally we will draw the magnitude plot and phase plot. First, in this chapters, we will discuss all about the magnitude plots. Only we will consider the magnitude plots first. Magnitude plots for different kinds of system, right? So this is one kind of system is given to you. Say gs is equal to 50 by s plus 2 into s plus 5. This is a system transfer functions given to you, right? So if this is your transfer functions, now what you have to do, we have to first of all consider the sinusoidal transfer functions, that is j omega. So put s is equal to j omega in these transfer functions. So what will get, this is your j omega, that is 50 by j omega plus 2 j omega plus 5, right? So next step, you see, this is a second order system and type. One of the most important parameter to start with the Bode plot is that you have to find out the type of the system. So type of the system is very important. So what is the type? Here there is no pole at s is equal to 0. See, this is a type 0 system. So what we have done till now, we have considered any system which is having first order factors only. So this is, first of all, there are two poles which are lying on the left hand side of the S-plane. That means the minimum phase system. The concept of minimum phase is now clear. Now we have to get the sinusoidal transfer functions, that is j omega, that is 50 by j omega plus 2 into j omega plus 5. That we know. Next, we have to find whether this system is type 0 system, type 1 system, type 2 system, type 3 system, and whatever the different kinds of system. So this is the type 0 system, right? Next, the next step is to find the time constant form. Time constant form. Time constant form means, you know, from the time response analysis, any system functions 1 plus st expressed as any factor, any first order factor. This is 1 plus st. And once this form is available, then the Bode plot is possible, because that is a asymptotic plot, where asymptotic plot, and also actually we are getting the frequency domain analysis through the Bode plot. Frequency response analysis means we can vary the frequency from, say, low frequency to high frequency. That means actually in case of Bode plot, roughly speaking, what happens, there is a low frequency part, that means omega is very less than 1 by t, and one is a high frequency part, that is omega is very greater than 1 by t. So what will get, omega t very less than 1 and omega t very greater than 1. These are the true conditions. If the two conditions are given, so there is definitely a point of intersections, right? So there is a point of intersections where these two asymptotic curves will may meet. So this is known as corner frequency. What is known as? This is known as corner frequency, and this is very much important. So this corner frequency, concept of corner frequency means what? See, we have considered the two range of frequency. One, omega is very less than 1 by t, and omega is very greater than 1 by t. So 1 by t is the frequency which is known as the corner frequency. 1 by t is the frequency where if these two curves can meet, right? So that frequency is known as corner frequency. That means the meeting point of the two slopes, basically meeting point of the two slopes. Maybe the graph is like this. This is, say, one slope, one straight line, another straight line is like this. So this point is known as the corner point. As this is a corner point, so this will be having one frequency, and that frequency is known as, say, 1 plus s by omega, right? Because t is equal to 1 by omega. 1 by frequency is equal to time constant, right? So this 1 plus s by omega form is required to find out where this slope and this slope will meet. So two slope must have to meet at a point which is known as the corner point, and the frequency at which this low frequency asymptote and a high frequency asymptote will meet, that point is known as the corner frequency. And frequency is just inversely proportional to the time constant. So time constant, if you express any form like, say, s plus 5 in time constant form, we have to express this in time constant form. Once the time constant is obtained, that means you can get the corner frequency for that particular factor, right? That means, say, this is expressed, I will write it like, say, 5. If you take 5 common here, then 1 plus s by 5, right? So this s plus 5 can be expressed like 5 into 1 plus s by 5. Once this is expressed, you see 1 plus st. So this is 1 plus st form. 1 plus st form means, what is the time constant? That is 1 by 5. 1 by 5 is the time constant. If 1 by 5 is the time constant, what is the frequency? 5. So you would get the corner frequency associated with this term. And until unless time constant form is not possible, so you will not get the corner frequency for that, right? So if you not get the corner frequency, then how this slope will be? Actually, asymptotic plots will be possible, because we are going to get the straight line approximation of the actual graph. Again, I am saying straight line approximation of the actual graph. So straight line approximation of the actual graph means we have to go for the connection of the defined slopes. So once the defined slopes will be connected, so how which point is where they will meet, that point is corner frequency, that must have to be known. So for getting the corner frequency, you have to express this in the time constant form, right? So what are the 3 steps? I will just take this example again, and step by step follow what I have to do and how to get this concept of corner frequencies and all this for each of the factors, right? So this example is related like 50y is plus 2, it is plus 5. This is a time zero system first of all. Next, express this in terms of time constant form. Express it in time constant form. So how the time constant form will be obtained? 1 plus st form. Time constant form means 1 plus st form, right? So we will just rewrite this transfer function gs is equal to 50. You just take out 2 as the common factor. So 1 plus s by 2. Similarly, multiplied by, you take 5 count out of it, we get s by 5, right? So what is actually you are getting? This is 5 by 1 plus simplification s by 2, 1 plus s by 5. So this is 1 plus st1, this is 1 plus st2. So this is one first order factor, right? This is first order factor where time constant is equal to 1 by 2. If you compare this with 1 plus st form, so what is the value of t? 1 by 2, right? So this is the time constant form, and you see similarly this is also a first order factor with time constant t2 is equal to 1 by 5. So once the time constant is known to you, then the corresponding corner frequency associated with it, so omega 1, that is, I can say it omega 1, that is 1 by t. So omega is equal to 1 by t, right? So 1 by time constant will be the frequency. So omega is equal to 2 radian per second. 2 radian per second. Similarly, omega 2 is equal to 5 radian per second. So this is the procedure how from any given transfer function you can get the time constant form. That means gs is the time constant form is expressed like this, and corresponding to each of the factor we are going to get the corner frequencies, right? If there is any factor which cannot be expressed in time constant form, the corner frequency is actually not available for that, right? So corner frequency calculation is not possible. So till time what we have actually come to know, that is a time zero system, and time constant form is like this. Corresponding to that, what are the factors we get? This is the corner frequencies, right? And next is that for there are certain rules to draw the Bode diagram, and for the Bode diagram, the rules I will write side by side once we will go for actually calculating all these terms. So time constant form is known to us. Next step, we will convert this time constant form into the sinusoidal transfer function form, right? So we get the corner frequency corresponding to this factor is equal to 2, and corner frequency corresponding to that is equal to 5. That much we know, and we get g j omega by putting the time constant form, that is s is equal to j omega. If we put s is equal to j omega in the time constant form, we get 1 plus, this 1 plus form is required. So 1 plus s means j omega by 2 into 1 plus j omega by 5, right? So what we're getting, we are getting the sinusoidal transfer functions like this. So what is the requirement of sinusoidal transfer functions? Because once you convert this transfer function into the sinusoidal transfer functions, what you are getting? You are getting, this is a complex quantity which is functions omega. Now first of all, after getting this, we have to get the taking mod on both sides. Both sides. If we take mod on both sides, we will get, so mod of g omega, that is equal to your 5 by mod of 1 plus j omega by 2 or 1 plus j omega by 5, right? That means 5 by root over 1 plus omega square by 4 a square plus b square. So real square plus imaginary square. Root over of real square means 1 square plus imaginary means the coefficient of the imaginary part omega by 2. So this is omega square by 4, and this is equal to 1 plus omega square by 25, right? So this is your g omega, mod of g omega. Once you get this mod of g omega, that means the magnitude part you get from here. Actually, we are dealing with the first sections. Already we have discussed that in the first sections we will consider the magnitude plot and how to draw the magnitude plots or the Bode plot part, right? And so this is your magnitude, and this magnitude, you know, in the semilog graph paper when we have discussed, the magnitude was expressed as dB. So decibel. So decimal is expressed, that means any quantity, say 5 is your quantity, so you take log of this and take 20 multiplication on this to get it in dB, right? So conversion of the dB is that when you get the magnitude of certain quantity, then you have to take the logarithm on both sides. So to get log of g omega mod of, and after that you multiply the 20 on both sides to convert it into the decibel value, right? So here also we will do the same actions. That means we will take the logarithm on both sides and multiply by 20, right? So log of mod of g omega. So log of mod of g omega is equal to, you see, this is log of 5 minus log of 1 plus omega square by 4 half minus log of 1 plus omega square by 25 half, right? Now 20 log of mod of g omega, right? So this will be equal to 20 log of 5 minus 20 into that half into log of 1 plus omega square by 4 minus 20 into that power half will come in this side, that is log of 1 plus omega square by 25, right? So that part you see. So that means we have expressed the magnitude in dB. Now this can be known as magnitude in dB. So magnitude in dB is like this. So magnitude is dB in general form. This is the general form. Now for drawing the Bode plot, initial magnitude have to be considered. Next part is to get the magnitude at initial frequency. So this is your general part. Say for example, this is question number 1. Now what you have to do, we have to get the magnitude at initial frequency. So consider the graph again, which already we have discussed. Initial frequency. What was the initial frequency we have considered? We have considered 0.01 radian per second. So this was the initial magnitude, initial frequency I have considered in our strategy. Or you can take any other frequencies. Maybe you can take the frequency at 0.1 also, you can get 1 also. So that is of no issue what kind of frequency you are going to get. So initially, normally in all cases we will consider the omega. This is the convention, or you can take it as the thumb rule, that omega is equal to 0.01 radian per second. And once you put this value of 0.01 per radian per second here in equation number 1, then you will get m at omega is equal to 0.01. That means in order to start your magnitude curve, so drawing magnitude curve, you need to have the initial magnitude where you can start. So at omega is equal to 0.01, if you put this value omega here, what we will get, that is 20 log of 5 minus 10 log of 1 plus 0. Squared, that means 0.01 by 4 minus 10 log of 1 plus 0.0001 by 25. So almost this part is equal to 0, or you can get this part nullified. So am in dv, actually this is in dv, so that is equal to 20 log of 5. So this is 20 log 5, almost 20 log 5 dv. So log of 5 means 20 log 10 is 20 minus 2, 6, almost that is, you can take it as 14 dv, right? So this is nearly 14 dv, so we get the value like this. Now we will see why this value is required, because we have taken the example of this kind of system, and we will try to draw the complete magnitude plot corresponding to that, right? So this is a type 0 system where each of the two first order factors will be having the corner frequencies omega 1 and omega 2, right? And there is no zeros here, only the poles here, right? Now the next step, what we have to do, we have to consider one table. I will make a table. So what will be the content of the table? First of all, we will consider the factors. What are the factors associated with these transfer functions? With these transfer functions, what are the factors? So first of all, we will consider the factor. Next, we will consider what is the factor is for. Either this is for pole or this is for 0. For each of the factor, what is the slope contribution? This is slope contributions, right? This is the slope contributions, and each of the term will be having some corner frequency. And next is the cumulative, we may call it cumulative slope, right? So these are the total contents. That means, what are the contents? First of all, we will consider factor. What are the different factors? What are the factors we get in here? We will not consider this as the factor. We will consider this s plus 2 as the factor, right? Or whether this is located on the numerator or on the denominator. What is this? That means this is a pole. This is for pole. That means whether this factor is coming for pole or coming for 0. If this factor lies on the numerator, you see this can be 0. This is pole. And for a single pole, the now next is the hypothesis. What is that? That means for single pole, slope is minus 20 dB per decade. Here is the part, what is the already we have discussed in the first class, the requirement of the slopes for each of the pole. For single pole, okay, for we can say it as the single pole. For single pole, the slope contribution is minus 20 dB per decade. For single 0, this will be plus 20 dB per decade. Next, this is single 0. Slope contribution is plus 20 dB per decade. So slope contribution is minus 20 dB or plus 20 dB depending upon the factors. Either this is for 4 or this is for 0. So what is the slope contribution here? This is a 4. See, so slope contribution is minus 20. The slope contribution in decade for dB per decade. So I will not write the unit here. This is minus 20. And what is the corner frequency associated with this factor? This is corner frequency, you see, this is omega is equal to 2. This is in radian per second, right? So corner frequency is in radian per second. You can say this is dB per decade, right? And cumulative slope, that part I will discuss later. That part I will just make it remain blank. Next part is that you see there is another factor, which is again first order factor. First order factor means there is single pole. So if this is single pole, here, because s plus 5, this factor lies in the denominator. So this is a fold. Again, for a single fold, this is a single factor. So single fold, single pole means minus 20 dB per decade is your slope contributions. And what is the corner frequency associated with it? This is, you see, 5 radian per second, right? So what is the cumulative slope contribution? That I will discuss later. Okay, so the table structure is common to all the problems, right? So maybe this factor is s plus 10 is on the numerator. That means s plus 10, that will be for 0, and for a single 0, this slope contribution was plus 20 dB per decade. In that case, that was been written like plus 20 dB per decade, and the corresponding corner frequencies like this. So similarly, all the factors will have to be considered, right? All the factors means that factors which can be considered in the time constant form, or expressed as the time constant form, right? And see, for example, if there is a second order factor, how this will look like. For example, I am taking the example, I will take a later on the example, like say for example 50 by s plus 2 into s square plus 4s plus 2. So this is the second order factor, right? So in that case, you have to write the factor here, s square plus 4s plus 2. Corresponding to that, what is the corner frequency? That how to get the corner frequency, I will just let you know. And next part is that how many poles are there associated with this factor? There is definitely 2 poles, right? For this factor, what is the total number of poles actually this factor contributing? This factor is contributing 2 number of poles. If the 2 number of poles, that means total slope contribution will be minus 40 dB per decade. Total slope contribution minus 40 dB per decade, because each of the pole added, that means minus 20 dB per decade will be added. For that means, see, for double pole, now the question is for double pole, for any factor double pole, slope is minus 40 dB per decade, right? For triple pole, minus 60 dB per decade, right? For double zero, this is plus 40 dB per decade. For triple zero, this is plus 60 dB per decade. So this is how the slope contribution for each of the factors associated with the transfer functions can be determined. So s plus 2, s square plus 4s plus 2, s square plus 6s plus 8, like this, all the second order terms will be having 2 poles and the same factor. That means it will contribute a slope of minus 40 dB per decade. If that factor lies on the numerator, that contributes a that slope is plus 40 dB per decade. So that is the total contribution of slopes, and how the corner frequencies are calculated for first order factors already we have discussed. So this is your table. Now we know 2 corner frequency, initial magnitude, and some table is actually in front of us. So based on this, how can we draw the Bode plot, right? So you know, this factor, this table is very much important to draw the Bode plot, and I will just remove this part here, and we'll show how this can be actually drawn in these sections. You know, there is space content. For space constant, what we have taken, we have removed rest part of this table, and you know, this s plus 2 is the factor and s plus 5 is the factor. For example, I'm just going to show how to draw the Bode diagram, and that is for pole, this is again for pole, and for every pole we know the angle contribution, or slope contribution is minus 20 dB per decade. That is known to us, and corner frequency table is very much required, and this cumulative slope, how this can be drawn. So the thing is that till time, that is omega 1 is equal to 2, we know omega 2 is equal to 5, and initial magnitude was 14 dB. That much of data is available to us. So we will try to draw the Bode plot here. So I am trying here very small part of the graph like this, where you see this is your omega is equal to 0.01 initial frequency, And so this graph is 0 0.1, 0 0.1, 10, 100 and 1000. And according to our style or system, how we will draw this Bode plot, what we have considered the last decades. That means maybe 100 to 1000. This is our last decade, where we have drawn the 3 slopes. Maybe 4 or 5 slopes can be drawn here. You see there are 3 slopes I have drawn, but I have drawn 0 dB to minus 20 dB. That means this is downward slope. So this slope is having minus 20 dB per decade, right? Again I am saying this is plus 40 to 0. So this is downward again. Plus 40 to 0 means minus 40 dB total change of slope, right? So plus 40 to you see this is a plus 40 to 0 dB. That means this is minus 40 dB per decade slope, this slope. And this is 0 dB to plus 20 dB. So 0 dB plus 20 dB means what you are getting? You are getting that slope is equivalent to plus 20 dB per decade. That are the different slopes you can draw here as your reference slope. So this slope we will call it as the reference slope, right? So these are the reference slope which will be drawn at the rightmost decade, right? Next, start with this magnitude. What is the magnitude? 14 dB, where the 14 dB at omega is equal to 0.01. So in this frequency magnitude is calculated, right? So calculation steps are shown. So this is 14 dB. So 14 dB is something here. You can say this is your 14 dB, right? So this is your starting value of the magnitude. Now from here what you have to do, now once you identify the initial magnitude, next this we know a type 0 system, right? This is a type 0 system, and type 0 system is required. Why? Because for type 0 system initial slope is equal to 0 dB per decade. Type 0 means initial slope is 0 dB per decade. What does it mean by this term 0 dB per decade? 0 dB per decade, you see, any decade, you can consider any decade. Any decade means from 1 to 10, for example. So 1 to 10, this is one decade, and slope is 0 dB per decade. What does it mean? That means the magnitude change is 0 dB when there is a change in frequency 1 decade. So 0 dB magnitude change for 1 decade frequency change. So frequency change from here to here, our magnitude change is 0 dB. 0 dB means the initial magnitude and final magnitude both are same. So what is the nature? So this, what is the slope of this? 0 dB per decade. That means 0 dB per decade is a line which is normally parallel to x-axis. As simple as that. So 0 dB per decade is nothing but a straight line which is having slope 0 dB per decade. That means this is parallel line which is parallel to x-axis. So this is the concept of 0 dB per decade. And for type 0 system, now coming back to our system, that system is type 0 system. If the system is type 0, that means what we have to do? We have to consider that the system's initial slope is 0 dB per decade, right? Initial slope is 0 dB per decade. If this is type 1 system, initial slope was minus 20 dB per decade. If this is type 2 system, initial slope was minus 40 dB per decade, right? So initial slope versus type, I will write a table here, right? And from that we will consider our system. So we have considered one table. From this table it will be a bit clear that if the type is of 0, that is type 0 system, initial slope will be your 0 dB per decade. If the type is first type, that is type 1, system is having type 1, that means initial slope was minus 20 dB per decade. If the system is type 2, minus 40 dB per decade. If this is type 3, minus 60 dB per decade, and so on. That means addition of one pole at s is equal to 0. Time increases means what? Type increases means the number of pole is added at s is equal to 0, that is at origin. So at origin, if the number of poles are adding one by one, that means this slope contribution is just changing like -20, -20, -20, and so on. So for type 0, 0 dB per decade, 1 type -20 dB per decade, type 2 -40 dB per decade. Now in this case our system is of type 0. So initial slope is 0 dB per decade. If the initial slope is 0 dB per decade, that means up to which that means initial frequency is at omega is equal to 0.01, right? So from 0.01 you have to draw a straight line which is parallel to x-axis. That means the initial slope is 0 dB per decade. So we will draw a straight line parallel to x-axis, right? So this is your 0 dB per decade, right? So this is your 0 dB per decade. There is no problem. And how much this line will be extended? That line will be extended up to the point of minimum corner frequency. Up to the point of this line will be extended up to minimum corner frequency. So here, what is the minimum corner frequency? From the corner frequency table, you see the minimum corner frequency is 2. So if this line is to be extended up to your point which is 2. So this line is to be extended up to 2. From here you see there will be point 2, for example. So this will be point 2 corresponding to that. So actually up to minimum corner frequency means here up to 2 radian per second. So 2 radian per second, this slope, that the 0 dB per decade slope will be extended to this point. So this is the omega is equal to 2. So this is omega is equal to 2. Up to omega is equal to 2, the slope will be 0 dB per decade, right? So once you reach here, what you will see, there is a pole. Okay, so once there is a pole, for its own contribution for a single pole -20 dB per decade. So if this 2 radian per second is coming due to single pole, and for pole, what is the contribution? Its own contribution is -20 dB per decade, that you can see from this table. So initial frequency, that is slope, was 0 dB. So this 0 minus plus of -20, that is -20 dB per decade is your cumulative slope. Cumulative slope means what? Cumulative slope means at this -20 dB per decade, this graph will start from these positions, because this is the positions at omega is equal to 2. Up to this we have reached, and here you see this is a pole. For a single pole, the contribution is -20, and before that, what is the contribution? 0 dB per decade. So after this, what will be the slope? This will be -20 dB per decade. That is known as the cumulative slope. So you will go parallel to -20 dB. So this is your -20 dB line. So go parallel to this. Just make a parallel line to it. So this parallel line actually will be having slope of, you see, this is -20 dB per decade, right? So this is, and how far this line will be extended? How far this line will be extended? This will be extended up to the next corner frequency. Up to next corner frequency. So what is the next corner frequency? In this table, the next corner frequency is 5 radian per second, right? So this will be extended up to 5. So here you will get the point 5. Here you will get the point 5. So up to 5 radian per second, this is your omega is equal to 5. So once you reach there, this line is not much required, right? So here what we will find? Here you will again find a pole, right? Once there is a pole, for a single pole contribution is -20 dB per decade for its own pole, and previous slope to this point, corner frequency. Corner frequency means where the two straight lines are meeting. So previous slope was -20 dB per decade, and next again for this pole, what is the contribution? -20 dB per decade. So what will be the cumulative corner slope then? Cumulative slope will be, you see, this is -20 previous, plus or minus 20, that is minus 40 dB per decade, right? So ultimately from this omega is equal to 5, we will have to draw a slope of minus 40 dB per decade. This is minus 40 dB per decade. So this minus 40 dB per decade, you see, you will have to draw a parallel line to this minus 40 dB per decade. This is your minus 40 dB reference line. So parallel to this line, if you draw a line, so this line, see, this is your line. So this is the slope which will be known as minus 40 dB. So this is your minus 40 dB per decade, right? So this is your omega is equal to 5 line, this is omega is equal to 2 line. So these are the three slopes we get, right? So this is 0 dB per decade line. Initially, due to the type 0 system, this goes up to the minimum corner frequency of the table. So minimum corner frequency you find, this is 2. So once you reach to 2 corner frequency from this graph, you see this is a pole. For a single pole, slope contribution is minus 20 dB. Initial slope was, previous slope was 0. So cumulative slope, you see cumulative slope is the addition of the slope of the previous slope and current slope. So this is minus 20 dB as a whole. So minus 20 dB line is parallel to the minus 20 dB slope, standard reference slope. You draw up to the next corner frequency, that is omega is equal to 5. Once you reach to the 5, you see there is again a pole. For a single pole, again the contribution is minus 20 dB per decade. And once the contribution is minus 20 dB per decade, what is the cumulative slope you get? Previous slope was minus 20 dB here, and next for this pole a minus 20 dB contribution, that means 2 will be added. So to get minus 40 dB per decade, once you get minus 40 dB per decade, you have to draw a line parallel to the minus 40 dB reference line, right? Just take either protector or 2 scales to get the parallel line. So this is minus 40 dB. You just extend it. So this is a kind of magnitude, asymptotic magnitude plot for the particular system I have considered. So that is the way how the magnitude plot for different kinds of system can be drawn, where the first order factors are available. Okay. In the next class, we will discuss another problem, and we will try to just repeat these steps so that it can make you more clear, so that how can this magnitude plot can be drawn. Okay. Thank you.